Chapter 6 here, which is sort of one chapter to talk about sort of equations and balancing equations. Then we'll lead up into types of reactions, which we'll tap next in the next chapter. All right, so remember a chemical reaction is a chemical change. Which means really what you start with and what you end up with is fundamentally something different. Something has formed. We did a couple of reactions or a couple of experiments that involve physical and chemical changes. So in those chemical changes, you really saw something new sort of form. And as we'll talk about, there's really sort of three reasons why a chemical reaction takes place. And we'll get into each of those in just a second here, but here are some evidences of maybe a chemical reaction has taken place. Sometimes we do see something that's visual, perhaps a color change, a solid is formed, bubbles, which usually indicate some type of gas has been made. And really, sort of, as I mentioned, the three sort of reasons why a reaction takes place is really one of these things are happening. Either a solid is being formed, either water is being formed, or there's basically electrons being transferred. So pretty much you could cut down, as we will see here, when we talk about different types of reactions, the way to classify reactions, you pretty much can find one of those three things occurring as they're really the reason why, again, a chemical reaction takes place. Either you're going to make a solid, your electron transfer, or water is being made. We can also sometimes feel heat coming off. So, for example, if you held onto a test tube and it gets really hot, that means it's sort of an exothermic type process occurring. It's releasing all that energy into your hand if you happen to be holding the test tube, and vice versa. If you're holding the test tube, it kind of feels cold to you. It's more of an endothermic type process. It's basically absorbing all the energy from your hand. Obviously, a flame would be visual, but again, the reaction basically of methane and oxygen. When we light a Bunsen burner, we get a flame, right? That's a combustion reaction that's basically taking place when we do that. So here, obviously, all these bubbles that are being formed here, these are all indications that a gas has been made. You also saw that, I think, also when we were doing chemical and physical changes reactions or experiments, you basically trap some of the gases or the bubbles, right? And you put your wood splint in there. So these are, again, some signs that a chemical reaction has occurred. And also here we do see sort of a color change indicating the presence of perhaps a new product that is there when the reaction of some colorless hydrochloric acid is added to a red solution. So obviously here something new was made. This was colorless, this was pink. Then obviously we get blue that's made on this side, which is, again, a difference of probably a chemical change has occurred, rather than if you started with something that's blue and added it to it, it may just be a physical change, right? Nothing new, maybe a form. This is an experiment we're going to do actually shortly. But this is basically led to iodide being formed, or this is actually some dichromate, I guess, but a very similar type of one. But again, here we pour these kind of solutions together and we get a solid that's being formed. Again, another reason why a reaction takes place. And obviously there's our hydrogen gas bubbling and our combustion. All right, so when we do have a chemical reaction that occurs, we do represent it with a chemical equation. And it's always important with chemical equations, as we'll talk about, is we always want to make sure that they're balanced. There's a couple important things for a chemical equation. There's the arrow, and then on the right-hand side of the arrow are our products, and on the left-hand side of our arrow are reactants. So it's always reactants to products when we write a chemical equation. we use basically the symbols and the formulas in the equation here. So for example, here we have hydrogen gas basically reacting with oxygen to form water in this case. You always want to make sure that you are definitely starting with formulas. And we're going to be talking about balancing equations, but it's really important to always have the right formulas down. Sometimes you're given things in words and people try to like balance the equation and write the formulas at the same time. And a lot of times you'll end up with the wrong sort of formulas. It'll never balance. It's very common in equations that happens when you, for example, have the reactants and you need to kind of predict what's on this side. So it's very common people try to do both of those things together. Always when you're doing equations, the proper order is correct formulas and then balance. So again, I want to kind of do it at the same time. When we look at this molecular oxygen to yield water, or we could say hydrogen gas plus oxygen gas makes yields water or produces water. That also is an important thing. Sometimes when you're arguing things in words and they say something like molecular oxygen or molecular hydrogen, remember that those are diatomic molecules. So they do come as twos. So you wouldn't want to write H plus O makes water. Again, those are not the right formulas to begin with. So you want to make sure you do get those right formulas down correctly. When we look at this, though, there is a little problem with this equation, and it is sort of the balancing aspect of it. We only in chemical reactions break bonds, which are our electrons. We never touch anything that's in the nucleus, which is our protons and our neutrons. And that means that when we have a chemical reaction that occurs, we do have conservation of the elements, which means if we start with like 4 carbons on the left, we really should end with 4 carbons on the right. They may be in different things, but we should never lose any elements along the way. So if we made like a little table here from our reactant side and our product side, and that's hydrogen, oxygen, we can see on the left-hand side, we have 2 hydrogens. Right-hand side, we have 2 hydrogens. Left-hand side, 2 oxygens, which are here. Right-hand side, 1 oxygen, which is there. So we can see in this case, this is not a balanced equation, as we obviously have more oxygen on one side than the other. So we can never lose anything along the way. So we do want to do the process here of balancing the equation. And we can see very easily by just putting really a 2 here in front of the H2O. If we make our little table here again, we have 2 hydrogens on the left, 2 on the left for oxygen. We now have 4 hydrogens, and this 2 also goes to this guy, which gives us 2 oxygens. We also now see that we kind of screwed up hydrogen, so we could also fix that by putting a 2 in front of hydrogen, and that gives us now 4 hydrogens and 2 oxygens. So the way that we go through and balance equations is we only really change the coefficients. So you should never change any number other than the coefficients that are in front. You should never change any of the subscripts, because if I change the subscripts here, I am changing what that is, right? So if I change that from a 2, it's no longer water. You should also never put any big numbers in between, like the formula and stuff like that. So only those coefficients in front. So by putting those 2's in there, that gives us really our balanced equation. And again, that is always what you want. So, you know, even if the problem really isn't a balance the equation type problem, but you're using the equation for something else, really the first thing you should always do is look at the equation and make sure it's balanced. If it is not balanced, then you definitely should go and balance it up. But that's always one of a balanced equation when you're using it. 2 parts of our equation here, as I mentioned before, the reactants, which are on the left-hand side of the arrow. That is really our starting material. So that is the stuff that is reacting together. And our products are the stuff on the right-hand side of the arrow. And those are the guys that are formed as a result of the chemical reaction that is taking place. So it's always, again, reactants going to products. And remember, again, the only thing that we're doing here is we're taking all the bonds over here and we're breaking them. And they're reassembling on this side and we're making bonds. So again, in a chemical reaction, that's essentially what happens. We break apart bonds, which involves our electrons, and we remake new bonds on the other side. We saw some of this, I think, some potassium, metal, and water, and so forth. As a catching on fire. These are a couple of ways that you could look at a balanced equation, and we'll use some of these in later chapters for some calculations. We could take our coefficients here that are in front, and obviously, like in most chemistry, if there is nothing written there, it's assumed to be 1. We could say that there are 2 molecules of H2 react with 1 molecule of O2 to form 2 molecules of H2O. Really, this next relationship is the one we'll use the most, and you will use the most in chemistry. It is what is sometimes referred to as the mole-to-mole relationship, and that says the same thing, just taking the coefficients for every 2 moles of H2, we react it with 1 mole of O2, gives us 2 moles of H2O. The last one is one we won't use too much in terms of calculations or anything, but this is sort of the idea of conservation of mass. We have 36 grams of reactants, and we should have about 36 grams of products. What that means is, in this case, the 2 hydrogens or the 4 hydrogens on the left have a mass of about 4 grams from the periodic table, and the 4 hydrogens on the right should also have a mass of about 4 grams from the periodic table. And our 2 oxygens on the left is about 32 grams, and our 2 oxygens on the right should also have 32 grams. So it's not necessarily how much you produce or started with, but the molar masses of each of the elements on the left and right should equal each other because they are the same numbers. Other important sort of abbreviations that we do see in equations are G, L, and S written next to the formulas. So G representing gas, L representing it's in the liquid phase, S representing it's in the solid phase, and I think it's on the next slide, but I'll put it here as well. AQ is aqueous, which means it's kind of a solution. There is a difference between liquid and aqueous. So something that is a liquid is a pure liquid. Like if you had water by itself, that would be considered a liquid. Something that's aqueous is really a solution and usually made by dissolving something in a solvent. So for example, if you took pure water and you added some sodium chloride to it, it would dissolve and you would make a sodium chloride solution that would get the aqueous symbol. So aqueous really does mean in most cases that you took 2 things together and they kind of dissolved together. They made a homogeneous mixture, which is a solution, but something that is a liquid is just one substance by itself. So a lot of times in formulas, we will include the actual states of everybody in there. In addition, although we do use chemical equations most of the time to represent a chemical reaction that takes place, we can use chemical equations to represent physical changes that do take place. And that's what we see here on the bottom. This is liquid water going to ice, basically, and that's liquid water going to steam. These are really physical processes, but we can also use equations to represent that occurring. On top of the arrow, sometimes catalysts are things that speed up. And a catalyst, not a product. It does not get used up in the reaction. So typically a catalyst is really just there to facilitate the reaction occurring a lot faster. Sometimes catalysts can just be metals. Yeah. So sometimes, like platinum or something like that. Catalysts could be like acids. So sometimes H+ is written up there to represent an acid being used as a catalyst. Other things that we sometimes do see on top of the arrow, Sometimes we will see water written up on top, and that usually indicates that you're dissolving something in water. And lastly, sometimes you'll see a little triangle written that sometimes represents heat is involved, or the delta symbol. So these are a lot of sort of the symbols that we see in chemical equations, and they're also included a lot of times as well. So again, here's that process. Clearly the arrow missed very badly there. So we'll put our arrow in here. Put water. So again, that would be the process of dissolving our sodium chloride. And again, this would make an aqueous solution, which again is different than water or pure liquid. Any questions on any of that there? So as I mentioned before, it is really important to always have the equation balanced. And again, sometimes they are given to you balanced, sometimes they're given to you unbalanced. I would say if you see an equation, you see no coefficients, you should definitely take a pretty good look at it to make sure if it's balanced or not. It may be. But I would say probably in most cases, if you do see an equation and there are some coefficients or numbers in front of things, then it's probably balanced unless they're trying to trick you. But in most cases, it would probably be balanced. But 100%, you should always double check really quickly to make sure it is. And if it's not, you then should definitely balance it. The first thing you want to do when you are going to balance an equation, and especially if you're given everything sort of in words, you, as I mentioned before, want to make sure that you have all the correct formulas down. So just like you're doing nomenclature and you're writing formulas, you want to get all the correct formulas down, regardless of the balancing part. Also really important, as I mentioned earlier, if you have to predict what's on the product side, again, you want to get the right formulas down first. Next thing you want to do is to balance the equation. Once again, we only change the coefficients in front. So the big numbers that come in front are the only numbers that you can change. Most people do sort of a trial error, put a number on one side, put a number on the other side, and eventually it all sort of falls into place. You could start with things that, in my opinion, are sometimes easier, just to start with things that are kind of the easiest to balance. You could just clearly see if I put a 2 here, it's going to balance it. Also, a lot of times you want to save elements that are in multiple things or multiple sort of formulas. So if you on one side have oxygen in like a couple of things, and on the other side you just have it in one thing, you may want to save the oxygen for the end to balance. So that's a little bit easier as well. So you're going to keep doing that till you've reached pretty much the same numbers on each side. And there's really two important rules to make sure that you have a correctly balanced equation. The first one is they all need to be whole numbers. So whole numbers for the coefficients. And they need to be the simplest set of whole numbers. So what do I mean by that? Let's just say you balanced an equation and it was like 2a plus 4b gives you 6c. And we just say, okay, this is balanced. Now, although it may be balanced, when I look at all the coefficients there, which are numbers in front, I could definitely go through and reduce everybody down by 2. And that's what you should do. So you could definitely come through here, basically divide all the coefficients by 2, which would give you a plus 2b gives me 3c. So that would be the properly balanced equation. And it does sometimes happen. Sometimes people can see maybe larger numbers and stuff like that. So the last thing you want to check, obviously, is that you have obviously the same number of elements on each side. All the coefficients are whole numbers. And secondly, if you can reduce down all the coefficients and still end up with whole numbers for everybody, that is the proper way to balance that equation. So you should definitely reduce it down. Any questions on that there? Okay. Another approach. Let's take a look at one here. All right, so let's take a look at this and we'll go through it here together. I'll show you the method I would use to balance this equation. I'm just going to rewrite it because it gives me a little bit more room for my coefficients. So personally, when I go to balance equation, the first thing I really do is make a table. So we have our reactant side, we have our product side, and we basically just list all the elements. So we have nitrogen, oxygen, and hydrogen. On the left-hand side, there is one nitrogen right there. On the right-hand side, there are two nitrogens right there. Left-hand side, one oxygen there. Right-hand side, one oxygen there. Left-hand side, two hydrogens there. And right-hand side, two hydrogens there. So a table is good for a couple of reasons. It can really kind of point you in the right direction. So clearly here, we could clearly see from our table that it is just the nitrogen at this point that is not balanced. So all we need to do is put a 2 in front of the nitrogen on the left-hand side. And if I do that, once again, it is going to be the coefficient. That does change some of the stuff here on the left-hand side. We're going to have now two nitrogens. Again, this 2 goes to here, and it also goes to the guy behind it as well. That means that we also now have two oxygens on the left-hand side, and here we have two hydrogens. So this is a very common thing that occurs as you're balancing equations. You kind of fix one thing, but frankly, screw up the other. So then we want to go really to what would be next, easiest to balance. And again, in my case here is obviously our choice is oxygens. So we're going to go to the right-hand side. We have two oxygens on the left. We need 2 on the right. So once again, we're going to put a 2 in front of it. That gives us 2 nitrogens. Once again, this 2 goes to the hydrogen, also goes to the oxygen behind it. And that gets us for the oxygen 2. And for the hydrogen, we now have 4. At this point, we can clearly see we want to now go back to the side and fix our hydrogen. Easily be done by also putting a 2 here. And that will give us, again, 2 nitrogens, 2 oxygens. And once again, this gets multiplied back here to 4 hydrogens. Any questions on any of that there? So tables can be helpful, sort of organizes things for you, kind of gives you maybe some direction as to where to go do the table. But again, sometimes people find it helpful to do. Any on that there? All right, I tried one. Why don't you try then? So once again, we have our reactants, we have our products. We're going to got carbon, hydrogen, and oxygen. Once again, here on the left-hand side, there are 3 carbons. Right-hand side, there's just 1. Left-hand side, there's 8 hydrogens. Right-hand side, there are 2. Left-hand side, there are 2 oxygens. On the right-hand side, there are 2 oxygens here, and you don't want to forget this guy over here, which is 3 at that point. So once again, here we got oxygen in a couple places. At this point, I personally, again, would start with what looks like the easiest to me. Carbon looks pretty easy to solve, so we can put a 3 in front of the carbon there on the right. When we do that, that's going to give us 3 for the carbon. Once again, this goes to both of the guys behind it. So that's going to give me, for oxygen, 6 there, plus 1 more over here, makes 7. And for the hydrogens, we are still at 2. So we definitely fixed the carbon. So once again, here we have hydrogen and oxygens are not good. This is a situation, as I was talking about earlier, where if you have a choice, maybe where you want to go next. As I look at this, I do have oxygen here, and it's only in one place over here. So that's a lot of things sort of interwoven together. So I'm going to actually save oxygen for the end here and actually go at the hydrogen since it's only in one spot on each side. And that will make it much easier to balance. So by taking that approach and going with hydrogen first, I'm going to fix the hydrogen on the right by putting a 4. And that once again gives me 3 for the carbon. Also gives me 4 times 2 for the oxygen, which is 8. For our oxygen, I'm sorry, for our hydrogen gives us 8. For our oxygen, 3 times 2 is 6. And then we also have 4 more over here. So that is going to be 10. So again, in this case, I left the oxygen for the end, and it works out really nicely because now I could go to the left-hand side here and put a 5. And we got our 3 carbons, our 8 hydrogens. And once again, here, our 5 times 2 is 10 oxygens. Any questions on that there? The goal here is not to keep moving numbers, right? Put a number, change it, get a number, change it. So the goal here is to try to keep everybody there, and everything should at some point really fall into place as you keep putting these numbers. All right, let's try another one here. All right, balance this equation. Diboron trioxide reacts with water to form boric acid, which is BOH3. Okay, let's take a look. So once again here, if we have something in words as we were talking about, you definitely want to make sure you get the right formulas. As we should know, for like in a half hour, diboron would be a type 3 compound, which would be Be2. There we go. Trioxide means 3. Oh, plus some water here is going to form BOH3. So once again, we want to make sure that we do get the right formulas down here. Again, we can make a little table if we like. So we got a boron, oxygen, and hydrogen. Boron on the left, there are 2. On the right, there is 1. Oxygen on the left there are 3 here plus 1 here, makes 4. Oxygen on the right, we do need to distribute this into both guys that are there. So it does go into both of those guys that are there. And that would give us 3 for the oxygen there on the right. Hydrogen on the left, we got 2. And once again, distributing that 3 in will give us 3 there on the right-hand side. At this point, not much to work with on the right-hand side, so might as well start there. We could fix the boron really easily by just putting a 2 in front of it. So we will do that. We will put a 2 there. That will give us 2 boron. And once again, this 2 goes for everybody that is behind it as well. So when we get to the oxygen, we basically need to multiply the 3 in, and then 3 times 2 is 6 by multiplying it out. Same thing here for the hydrogen. We multiply the 3 in, and 3 times the coefficient in front, which would give us 6 as well. Clearly, we can't do much at all anymore on the right-hand side, so we're going to go to the left-hand side here. And once again here, I'm going to go with the hydrogen first, as it is just sort of in one thing on the left, right, and one thing on the right. So in that case, to fix the hydrogen here, I'm going to put a 3 in front of it. And when I do that, that gives me 2 boron. Oxygen is 3 here. And again, this gets distributed to both of them, which gives me another 3. And that will now give me the 6. And my hydrogen is 3 times 2 is 6. So by fixing the hydrogen, and this happens a lot, it also fixes the oxygen as well. So we would be balanced in this case. Any questions on that one there? Okay. All right, so let's take a look at another one here. All right, balance this guy up here, NH3 plus O2, NO plus H2O. On the left-hand side, we got 1 nitrogen. Right-hand side, we got 1 nitrogen. Left-hand side, we have 3 hydrogens and 2 on the right. Left-hand side, 2 oxygens. And once again, here we have 1 oxygen there and 1 there, which gives us 2 on the right-hand side. So it doesn't look too bad. Everything's balanced except for hydrogen. In this case, the common number between the 3 and the 2 is 6. So actually, in this case, we're going to put 2 numbers down. On the left-hand side, to get our hydrogen to 6, we'll put a 2. On the right-hand side, to get our hydrogen to 6, we will put a 3 down. And when we do that on the left-hand side, we now have 2 nitrogens. Once again, this going to everybody also gives us 6 hydrogens and 2 oxygens. Right-hand side here, we still have 1 nitrogen This 3 goes again to both, so that is 6 hydrogens. And in terms of oxygen, we have 1 there and 3 there, so that is now 4, I believe. At this point, we fixed hydrogen, but obviously messed up everybody else. So nitrogen would be the next easiest to balance. We could put a 2 in front of it. When we do so, that gives us 2 nitrogens. Once again, this is going to go to everybody back there. So that is 2 oxygens and 3 more on the right there. It gives us 5. And lastly, here we still have our 6 hydrogen. At this point, we've balanced the nitrogen, we balanced the hydrogen. It is the oxygen that is not balanced. Clearly, we cannot do anything with the oxygens over here as we already put numbers, and then it'll be a long journey if we start playing around with it. So we do need to basically make our 2 into a 5. And one way that you could do that pretty simply is to use a fraction. So if I use something like 5/2, that would give me 2 nitrogens. That would give me 6 hydrogens. And when I take 5/2 times 2, it equals 5. Yeah. And that would give me 5 oxygens. It is technically balanced, but can I leave it like that? I cannot. So this is a good example. You can absolutely use a fraction to balance an equation, but you cannot leave it. So you do have to clear the fraction. And to clear the fraction, we has to multiply by the denominator. I think they call that still. And that's going to give us 4NH3 plus 5O2 goes to 4NO. Water. Go. And if I didn't screw it up, like I almost did there, we should still be balanced. On the right-hand side there, we got 4 nitrogens. On the left-hand side there, we also have 4 nitrogens. Left-hand side, we have 4 times 3, which is 12 hydrogens. 6 times 2 is 12 hydrogens. And left-hand side, 5 times 2 is 10 oxygens. And 4 oxygens here and 6 more here gives us 10 oxygens. So we are balanced. So you will, in a lot of cases, sometimes have to use a fraction to balance it. It oftentimes happens like this, where you got kind of elements and 2 things on one side, and really the diatomic molecular version of it on the other side is very common where it happens. How do you choose the right fraction? Not too bad. The number on top is the number you need. Number on the bottom should match the subscript, basically. So that should match the subscript. If you remember, we needed 5. And that's what went on top, and this number match, and that's a good way to kind of pick the right fraction. Any questions on that there? All right, let's take a look here then. Try just a couple more here. Why don't you balance this one up here? Fe2SO4 3 plus a little sodium carbonate. Okay, let's take a look in on these. There's a couple of things happening in these that might make it easier to balance. When we look, we do see some polyatomic ions. Hopefully you recognize those. So we have some polyatomic ions on both sides. Actually, in all these here, we got some polyatomic ions sort of happening on both sides. And whenever you have sort of equations that have polyatomic ions, you definitely could go sort of element by element like we were doing. But sometimes it's a lot of like multiplying in, multiplying out, and all that kind of stuff. So a lot of times it's very much easier just to keep the polyatomic ions together and like balance them as like units. So for example, if I were to do the first one, you can really start with any one you like. It may work out better than the other, but I'll just start here with sulfate. There's 3 sulfates on the left. There's only 1 sulfate on the right. So to fix that, it would just be very easy to put a 3 in front of here. That gives me my 3 sulfates that I need. And by doing this method, this will also tell you where you should go next. So I put the 3 in front here. That also then gives me 6 sodiums, and that's really where I should go next. So I have 6 sodiums on the right, but only 2 on the left. So I'm going to put a 3 to fix my sodium. That now gives me 6 sodiums. Also gives me 3 carbonates, which is where I want to go next, but I already have 3 carbonates and I am done at this point. Yeah. So that's usually what will happen if you kind of keep the polyatomic ions together. Everything will sort of fall into place and you could just kind of balance them as whole units. Again, you could go individual element, but sometimes there's a lot to keep track of, kind of multiplying in, multiplying out. So if we kind of take the same approach down here on this one, I got a nitrate over here. I got 2 on the left, 1 on the right. So I'm going to start with a 2 over here. That gives me 2 of my nitrate. Once again, I now should go to potassium, which is 2. So going to the left-hand side to fix my potassium, put a 2 there. That gives me 2 potassium and 2 iodide, which is what I need as well. And I'm done again here really quickly. So it can go really quick to balance it. Lastly, here I have nitrate on the left, nitrate on the right, and we got sulfate on the left and sulfate on the right. So once again, I'll just start with the nitrate. I got 2 nitrates on the left, 4 on the right. To fix that, I'm going to put a 2 in front of my nitrate. That gives me 4 nitrates, also gives me 2 bariums, which is where I should go next. So I'm going to come over here to get me my 2 bariums. 2 bariums also gives me 2 sulfates, which again is what I need, and I am done at that point now. So again, this is a much quicker way sometimes to do it, and you want to do it when you have obviously polyatomic ions involved. We can't really do it with the other things, but polyatomic ions is definitely a much easier approach than kind of going individually. Any questions on any of that there? Questions on balancing equations? All right, that wraps up, I think, chapter 6.